This video goes through lesson 4 of our Unit 2 notes in Precalculus on applying sum and difference identities. In this lesson, we will start to use some of the more complicated identities that you do not have to memorize. These are on the back of your reference sheet that was distributed at the beginning of the unit. So the sum and difference identities are going to show us how to handle situations where we are trying to do something like we are right here, where we're adding two angles together inside of a specific trig function. And we can work with sine, cosine, or tangent when we do these. The first part of this is just trying to show you that when we have a trig function, whether it's sine, cosine, or tangent, we can't distribute that trig function to any sum or difference. So here's what I already have written out for you here. Let's just say that x is 30 degrees and y is 60 degrees. If we look at the sine of the sum of those in parentheses, that gives us the sine of 30 plus 60, which is the sine of 90. And we know that the sine of 90 degrees is equal to 1. If we take the sine of 30 degrees and the sine of 60 degrees separately, we get 1/2 and root 3 over 2. So if we sum them separately, we end up with this pretty complicated fraction here, 1 plus root 3 all over 2. And since this one up here is not equal to this one down here, 1 is not equal to 1 plus root 3 all over 2, we can see that it's not true that the sine can be distributed to the x and the y values. And trig functions aren't the only functions like that. If you think about squares and square roots, we know that a very common mistake in algebra is to think that if you have the quantity x plus y squared, that it's equal to x squared plus y squared. But that is simply not the case. You would need to write that quantity as two separate binomials and then FOIL them, okay? Those are not equal. So trig functions work similarly. This is just an example to show you that. So here are the formulas we're going to need to work with since we can't just distribute the sine functions and cosines as we just looked at in that previous example. These formulas are very complicated. That's why you're not going to have to memorize them. We have different formulas for sum, so all these with addition, and we have different formulas for subtraction for the difference identities. One thing I want to make sure it's clear, just because I noticed that it got kind of smushed together on your notes, is that this part of the tangent identities, that's not part of the formula. That's just kind of a separate qualifier, if you will. So if you look at the formulas themselves, which is this part that I hadn't circled there, this says tangent of alpha times tangent of beta cannot equal 1. The reason that has to be true is because then in both denominators we would get 0, and we know we can't divide by 0 because we get something undefined. So this formula only works when the product of tangent of alpha and beta is not equal to 1, or in this case over here, equal to -1. So we are mostly just going to work on applying these formulas with some of the unit circle values that we know, and that's going to help us evaluate the sine, cosine, and tangent of angles that are not on the unit circle but can be constructed from angles on the unit circle. One quick thing before I move to the next slide, as I'm looking at your notes, I'm noticing that the cosine difference formula didn't get printed on your notes packet that you have, so you're going to want to write that right in between the sine and tangent difference formulas on your note packet. So you might want to pause the video and take a minute to do that. Here in example 1, we have a really common problem that we will be asked to evaluate. We want to use the sum or difference identity, or a sum or difference identity, to find an exact value for, and as you can see, this one says cosine of 15 degrees. So 15 degrees, not on the unit circle, but if you look up at the top here, I've written out what some of our unit circle values are, not all of them, and of course in degrees, since this problem is in degrees. And if you look at like 30 and 45, if we subtract 30 from 45, we will get 15. So we can use a cosine difference identity in order to construct this answer that we don't have typically kind of memorized from the unit circle. There are oftentimes many ways to do these. So if you look, and if you took 60 minus 45, that would also give you 15 degrees. So that's another way to approach this problem, and you could continue on through the other quadrants and find many, many different ways. We should, however, all end up at the same final answer, regardless of which combination of unit circle angles we choose. So I'm going to first pick my combination that I want to use, and I like to just keep things easy and work in the first quadrant if I can. So I'm going to do cosine of 45 minus 30. And then I'm going to look at my identity sheet, because I'm not expected to memorize those, and find the cosine difference formula. And that's the one you had to write in, because I don't know why it didn't copy on your paper. The cosine difference formula has an alpha and a beta listed, as the rest of them do. And you're going to treat the 45 like alpha and the 30 as the beta. So we're going to do cosine of 45 degrees times cosine of 30 degrees plus sine of 45 times sine of 30. So we notice that the cosine formulas have the product of the two cosines, the product of the two sines, and then when the problem is subtraction, it is addition when we expand the formula, and vice versa. So next what you have to do is just go back to your knowledge of the unit circle, because all of these are unit circle problems, or unit circle values that we can evaluate. So we know the cosine of 45 is root 2 over 2. Cosine of 30 is root 3 over 2. Bring down the plus sign. Sine of 45, root 2 over 2. Sine of 30 is 1/2. And then simplify. So when we multiply fractions, we multiply straight across. Root 2 times root 3 is root 6. 2 times 2 is 4. And then root 2 times 1 is root 2. Again, 2 times 2 is 4. And when we add fractions, we need common denominators. The good news is we have them here, so we know the common denominator will be 4. And then we can only add radicals together, combine them when they have the same radicand, which is the number underneath the square root. And since 6 is different than 2, we can't combine them, so we just write them out as root 6 plus root 2 all over 4, and that gives us our final answer. This next example has the same directions, use a sum or difference identity to find an exact value, but this one is in radians instead of degrees, so there's a little more thinking to do. If you look over on the side here, much as I listed out common degree values on the unit circle on the last example, here I've listed some of our unit circle values in radians, and then in this column I've converted them into twelfths. 12 is the common denominator between 3, 2, 4, 6, and so adding these fractions together will often result in a denominator of 12. So this can be a nice kind of reference sheet that you can construct when you're doing these problems. So now I'm looking for, back to my problem here, two values that add or subtract to give me 11 pi over 12. And when I see on my list that I have 8 pi over 12 and 3 pi over 12, I know that I can use those two values in order to find my sum. So I'm going to rewrite this like I did the last one, as the sum of these two values, but I'm really going to be using the more familiar unit circle versions of those so that it's easy for me to evaluate them once I expand with the formula. So I'm going to do pi over 4 plus 2 pi over 3. There are other combinations you could use. This is just the first one that I saw. Looking at my reference sheet for the sine of theta, or the sine of alpha plus beta, the sine addition equation, because I had to add these two values to get the 11 pi over 12, the sum addition formula tells me to take the sine of the first value times the cosine of beta, the second value, and then it has a plus sign, the cosine of the first times the sine of the second. So the sine and cosine formulas are similar but different. The evaluating from here should feel familiar now. So sine of pi over 4, root 2 over 2. Cosine of 2 pi over 3 is negative 1/2. Cosine of pi over 4, root 2 over 2. Sine of 2 pi over 3 is root 3 over 2. When I multiply, I get negative root 2 over 4 plus root 6 over 4. And then they combine the same way the last ones did. So you're going to find with a lot of these that our answers feel very similar to one another. That's okay. That will happen. So the last type of this example that I want to do is a tangent problem. Much like our unit circle problems, tangent's kind of the worst because it's the hardest to simplify. There's just a little bit more going on, but that's why it's important that I think I go through an example here. So working in degrees, I'm going to go ahead and break that 165 up into 120 plus 45. So similar to the last two, thinking about unit circle values that will get me to the angle of interest. So tangent of 120 plus 45. When I apply the tangent formula, it tells me to take the tangent of the first plus the tangent of the second, divide it all by 1 minus tangent of the first times tangent of the second. So that's my second step there. 1 and then 2. Okay. Start to evaluate from here. I'm going to draw a little line so you can see where my steps start and end. Starting to evaluate from here, we know that the tangent of 120 degrees is negative root 3. We know that the tangent of 45 is 1. In the denominator, we have 1 minus the tangent of 120 again, so that's negative root 3. Oops, see the negative there. And then times the tangent of 45, which is 1. So in the numerator, negative root 3 plus 1. In the denominator, 1 minus negative root 3 times 1. In my next step, I'm just going to start to clean this up. So let's leave the numerator alone because there's not much to simplify. At least not now. And in the denominator, a couple things are going on. First of all, the negative root 3 times 1 is still negative root 3. And then 1 minus a negative root 3 is the same as 1 plus a positive root 3. So that minus minus becomes a plus plus. At this point, you really are pretty much done. The only problem is we know that we don't like having square roots in the denominator in math, so we need to get rid of that root 3. It isn't as simple as multiplying numerator and denominator by root 3 because it also has this plus 1 attached to it. So if we go back and use our Algebra 2 skills, you learned that if you multiply by the conjugate, which basically just means change the sign in front of the root, and you do that to top and bottom, that will get you to a place where you no longer have the square root in the denominator. So you'll need to FOIL these, distribute them, and then clean them up. So if we do that, so I'm just doing first outer inner last in the numerator, I get negative root 3 plus 3 plus 1 minus root 3. So to recap, negative root 3 times 1 gave me negative root 3. Negative root 3 times negative root 3 gives me positive 3. 1 times 1 gives me 1. 1 times negative root 3 is negative root 3. Then in the denominator, 1 times 1 is 1. I'll get a negative root 3 and a positive root 3 from the outer and inner terms. That's going to make them cancel, which is a good thing. And then positive root 3 times negative root 3 is negative 3. So again, one more time, 1 times 1 gives me 1. 1 times negative root 3 is negative root 3. Root 3 times 1 is root 3. Root 3 times negative root 3, negative 3. Combining all of the like terms that we can in both the numerator and denominator, the 3 and the 1 give us a 4, and then we have negative 2 root 3's in the top. In the denominator, the root 3's cancel. 1 minus 3 is negative 2. And finally, because we have negative 2 that can be factored out of the numerator, so think about working backwards. If we had negative 2 times negative 2, that would give me 4. Pulling the negative 2 out of the coefficient of 3 gives us a plus root 3. And then the negative 2's can cancel. And our final answer is negative 2 plus root 3. A lot of work for that little answer. But I warned you. Those ones are kind of the worst. But similar to the sine and cosine problems, a lot of these will work out to be very similar to one another. The tangent problems are similar to one another at least. So as long as you practice, you'll get the hang of it. Just a couple more examples, and then you'll be good to go. So in example 4, we want to rewrite these expressions as the sine or cosine of one angle, of a single angle. They look worse than they are. What you're doing in each of these is you're looking at what is presented and trying to figure out what formula would that have come from. So looking at your formula sheet, which one has sine and cosine, then cosine and sine, with a plus sign in between. And what you should see is that this is coming from the sine of the sum of those two angles. So the sine is the one that has both sine and cosine in each term. And when the sine is a plus sign here, it's also a plus sign in the formula. So working backwards, we can kind of condense it into just this expression. And then you know how to add. So sine of 22 plus 13, 22 plus 13 is 35. And that is all I'm asking you to do. I'm not asking you to find the sine of 35 because that's not a unit circle value. So you're done. Same thing with the next one. So here you're looking at which formula has cosine, cosine, and then sine, sine. Those are the cosine formulas. So we have pi over 3 and then pi over 4. And you've got to look carefully because the cosine formulas have the opposite sum or difference. So since this is a plus, this is a minus. And then getting your common denominators, and you can look back and kind of reference those fractions in twelfths that we had before. You combine the pi over 3 minus pi over 4 to get pi over 12. Last one, these won't always have numbers in degrees or radians. Sometimes they'll have variables. So C is similar to B in that it has cosine, cosine, sine, sine. So we know this comes from a cosine problem. We have x, and then we have 2x represented. There's subtraction in this problem. Cosines are the opposites. Looking carefully at your reference sheet, so you'll have a plus sign in the parentheses. X plus 2x is 3x. And that is it. So those definitely aren't as bad. The last two examples are proving other identities using the sum and different identities. So this is a proof, which means I'm going to try to show that the left side equals the right side. I'm not going to touch the right side. Hopefully when you look at this, cosine of pi over 2 minus x equals sine of x, you are recognizing that this is a co-function identity. So our co-function identities that we worked with a lot on our proofs have that pi over 2 minus x or pi over 2 minus theta. And since this is cosine, I told you just remember it goes with sine. But in class I did promise you that I would prove later to you why this is the case. Now that we've looked at sum and difference identities, we have the tools to do that. I'm going to take the cosine of pi over 2 minus x and apply the cosine difference identity. So the cosine subtraction says cosine of the first times the cosine of the second. Remember the sign is opposite, so that's a subtraction. Here we have a plus. Sine of the first times sine of the second. Yes, you have some variables here with the cosine of x and sine of x, but you can evaluate cosine of pi over 2 and sine of pi over 2. We know that cosine of pi over 2 is 0. I'm just going to bring down the cosine of x right now. Sine of pi over 2 is 1. Bring down the sine of x. Since 0 times cosine of x is 0, 1 times sine of x is just sine of x, and 0 plus anything is itself, we can prove now with the difference identity why the cofunction identities are true. So for the last example, it's not our cofunction identity, but it's a similar idea in that we're just trying to show that the left side equals the right, and we have an addition problem. So we're going to prove that this is true. If you take a look at what this is showing you, x plus 2 pi, taking any angle x and adding 2 pi to it, 2 pi is just going an additional revolution around the unit circle. So it's basically, this is showing us to or asking us to prove that coterminal angles have the same sine values. It's a sine problem and it's addition. So the addition sine formula tells me to do sine of the first cosine of the second plus cosine of the first sine of the second. Evaluate the ones you can. So sine of x, just bring it down, times cosine of 2 pi is 1. Cosine of x times sine of 2 pi is 0. Sine of x times 1 is sine of x. Cosine of x times 0 is 0. Sine of x plus 0 is sine of x. So you have proven another identity using, again, the sum and difference identities. Those are the 3 types of problems that you're going to be asked to do on your assignment. So give that a try before next class, and we will discuss your questions then.